All right, so we're back on Earth now. This is the North Pole. So you're looking at a slight cross section of the Earth from the North Pole. Okay, and you guys know that the Earth rotates once in 24 hours. So this point on the surface of the Earth is going around once in 24 hours. Okay. So here's the following idea. If you have some object up there, a satellite, whose orbital period is also 24 hours, this is a very useful device. And why is that? It's useful for communication. You can send a signal there and back there. You know exactly where this object is. Okay, so you can send a narrow beam of signal, okay, meaning you're not wasting too much energy and you're efficiently communicating between these people and these people. Thousands of miles away without having to put wires. Putting wires is an extremely expensive thing to do. Okay. All right, this is what is called a geostationary satellite because it remains fixed above that point on the Earth. Okay. And this is only possible if you're right above the equator. And you also have to go around in the same direction as the Earth is spinning. Okay, this orbital height, it turns out, is 36,000 kilometers roughly. So if you have a satellite that's at a height of 36,000 kilometers, it takes 24 hours to go around the Earth. Okay. Now let's make sure we understand one fact. So let's say here's the Earth. Here's a satellite going around the Earth at a height of 36,000 kilometers above the Earth. How long does it take? 24 hours. Here's a satellite going around the Earth at a height of 36,000 kilometers. How long does it take? 24 hours. Okay. But these guys are not geostationary satellites. The Earth is spinning, and those guys, their location above the Earth will change. Only this guy will be about the same location. You guys understand that? Okay, so those are the useful guys. And we've said this before. So here's a picture of the satellites. So there are the geostationary satellites. Okay, and they are at 36,000 kilometers above the surface of the Earth. And that is the most expensive parking spot. Okay. So each country is allocated space there. Okay. And every country has their own satellite up there. And you guys, Mr. Musk has been launching many satellites, and if you keep track of that, you'll see that he's been launching geostationary satellites for various countries. Whenever Falcon Heavy goes, that's what it's doing. Okay. A lot of times. It's launching geostationary satellites or heavy payloads. Okay. So for geosynchronous satellites or geostationary satellites, the orbital speed is 3 kilometers a second. What was the orbital speed of, so orbital speed goes off as 1 over square root of R2. What was the orbital speed for the space station? 8 kilometers a second. So the space station is much closer to the surface and it's traveling faster. The geostationary satellite is much further away and it's traveling slower. Okay. We won't worry about this. Okay. All right, so things are changing very fast. So people keep track of all the stuff that's going around the Earth. So there were 11,000 individual satellites orbiting the Earth at the end of June 2023. So just this year. A year ago, there were half as many. Of these guys, so of the 11,000, About 5,000 belong to Elon Musk, his Starlink satellites. Okay. And Elon Musk, his goal is to put up 40,000 Starlink satellites here. Yep. You guys know that you can buy internet service from him? Do you know how much it costs right now? $120 a month. All right, so I'm going to just tell you a couple of good stories, and then we'll end at this. So, Mr. Newton figured out tides. Yeah. So, what causes tides? I'm sorry? The moon's gravity. Okay. So, for instance, here's the deal. If the moon and the earth were point objects, you wouldn't have tides. Okay. The reason you have tides is the following. And okay, so the moon. So let's think of a pound of stuff. Okay. So the moon is attracting this pound of stuff. This pound of stuff is closer to the moon, so it attracts it with a greater force. This pound of stuff is further away, and this pound of stuff is even further away. Okay? So this pound of stuff is being attracted with the least force. Okay? Now, here's the fact. Here's what was neat about his explanation. Okay, this pound of stuff is being attracted harder than this pound, so this ocean bulges there. That's easily understandable. Why is this guy bulging?
Because of the centrifugal force.
The static friction force on water that was stay together.
So do you guys understand the question? So why is this guy bulging is a question.
There's less force on it. It's further away, so it's bulging in the other direction. There's less force.
So this is not bulging. This guy is being pulled away from that. That's what's happening. Okay. So let's illustrate this in a diagram. Okay. So let's say we'll just make up numbers. Okay. So here's the moon. Here's the Earth. Let's say it's pulling this pound with a force of 100 units. This pound is being pulled with a force of 102 units. And this pound is being pulled with a force of 98 units. Okay. Now, to understand this, let's say we'll reset our 0. Let's call 100 pounds 0. Okay, so what is the force on this guy? 2 pounds. The force on this guy is 0 pounds. What is the force on this guy? Minus 2 pounds. Okay, which is 2 pounds. Okay. And so you get the bulge like that. Okay, so Mr. Newton was the first guy to explain tides. So, and the way this force comes about is, if you go back to our diagram, this force is in that direction, this force is in that direction. Remember, this force was set to 0, so there's a component there. So this is high tide, this is low tide. Okay. And what matters is the following for tides. Okay, so the height, this depends on how hard you're being pulled in either direction. Okay. So what you're doing is you're grabbing the earth by the ears and pulling on either side. Okay. It turns out that the sun pulls much harder, but because the sun is so far away, the differential pull of the sun on either side of the earth is half that of the moon. Okay. So this differential pull, the force per pound over here compared to there, okay? See, for the sun, it's 5 times 10 to the minus 7. And for the moon, it's 11 times 10 to the minus 7, okay, on the Earth. So the moon's differential pull on the Earth is twice that of the sun, okay? So the moon causes, the moon's effect is twice as much on the tides. Okay? And it turns out that, so these are spring tides when this sun and the moon is lined up like this. You have high tides, I mean the tides are higher, and this tide is the same as that. When the moon and the sun are like this, they're working against each other, and these tides are the lowest. Okay? So neap tides are the lowest. This kind of stuff can matter. So if we are unfortunate that we have only one sun, if you lived on some other planet, you more than likely would have two stars in your sky. Yeah. But anyway, so stars can bulge, expand, and so on. Okay. And if this expanded and if this got too close to this star, stuff can fall into the other star. Yeah. And again, all kinds of crazy things can happen. This guy can, it can turn into a black hole and stuff like that. If he was a neutron star and he eats enough stuff, he can turn into a black hole. Okay. So here's the escape velocity formula. So if here's an object, here's a star, this is called the event horizon. Event horizon is where the escape velocity becomes equal to c. Okay, so it's called the event horizon because what is a horizon? Horizon is something you can't see past. So if you are living in this part of the universe, you can't see anything in this part of the universe. Okay, so this is your event horizon. You can see stuff from here. Okay. So what this is if you can take a star and squeeze it past the event horizon, it'll become a black hole. Okay, and all the stuff will fall to the center. Okay, so this radius, called the Schwarzschild radius, the event horizon, is given by this formula. At this location, the escape velocity becomes the speed of light. Okay, I'm going to pause a second and I'm going to tell you about gravitational waves. Oh, here's something neat. You guys see these two objects? This is a picture of two bright objects out there in the sky. So some telescope has taken this picture. Well, it turns out that they're the same object. Did you guys hear that? Well, how do we know it's the same object and not two objects? So here I'm telling you that, so we're looking at the sky, we took a picture, and here's one bright object, here's another bright object. We took a picture of that. To me, it looks like two objects, and then I'm telling you it's the same object. How do we know? So what you can do is, you look at the intensity of light for various colors, okay? And let's say you get a graph like that. And the graphs are identical for the two objects. Well, so it is the same object. So what's going on is a question. So Einstein was able to explain this. So let's say here's a massive object, and Einstein, when he came up with this theory, he was able to say that, one of the things he said was, just like gravity bends mass, okay, gravity will bend energy. Okay, so Einstein was, there. So you see, one of the things Einstein predicted was, here's a star, light coming close to the surface bends like that. Now, you are hardwired to think that light travels in a straight line, so you'll see there the position of the star to be there. Okay? So this is the gravitational bending of light. And so quasars are extremely bright objects. So here is a light being bent like that. Here's another ray being bent like that. And you see these two images of the quasar. And that's what's happening. So this is called gravitational lensing. Okay. So anyway, there's all kinds of stuff. All right, before we finish, I want to tell you this cool story about gravitational waves. They were, again, like I said, we've been looking for gravitational waves since the 1960s, at least seriously, okay, or maybe even 1940s. And we first detected the gravitational waves in 2015. So a lot of hard work has gone in. Okay. All right. So here's the deal. You take a charged particle and make it oscillate like this. And you guys remember you attach a mass to a spring and it'll oscillate. So grab hold of a proton or an electron and jiggle it like that, and it will emit electromagnetic waves. Okay. So your FM station that are 100 megahertz or stuff, that's megahertz is 100 million, a million megahertz. So somebody is grabbing hold of an electron and jiggling it 100 million times a second. And you're getting that signal. Yeah. You can hold your wrist and jiggle your wrist like that, and you'll send out gravitational waves. Yeah. So make a mass oscillate, and you'll send out gravitational waves, except that these would be so weak you'll never be able to detect them. You want to detect these, you got to jiggle a massive object. Okay, well, you can take a black hole and jiggle it, and it'll send out gravitational waves. Well, how do you jiggle a black hole? You take another black hole. They go around each other, and that's essentially a black hole jiggling, and this gravitational wave goes up. All right, well, this gravitational wave passes by. What does it do? Okay, so if a gravitational wave passes by, let's say you have a circle of marbles. You have a circle of marbles. This circle will, space between them expands. In one cycle it will be like that, and another cycle it will be like this. Okay, so this circle is expanding this way and oscillating like that. And we want to measure this. Okay, well, this is exaggerated. You guys remember the distance between our star, 5 light years. How much did it expand? The width of your hair. Okay, and we want to measure that. So 1 meter will expand by plus or minus 10 to the minus 21 meters. The size of an atom is 10 to the minus 10 meters. The size of a nucleus is 10 to the minus 15 meters. The size of a proton is roughly 10 to the minus 18 meters. We want to measure the expansion by 1,000 times that. Absolutely mind-boggling. So how do we measure this is the question. You guys understand what I'm saying? So the idea is the following. Okay, so you take a light beam. Here's one beam, and here's another beam. Okay, so if one reaches with the crest and another reaches with the trough, at this spot, they'll exactly cancel each other and it'll be dark. Okay? Now, you guys understand that? Okay, now if this guy travels a larger distance, then there will be a slight mismatch and you will see light. Okay, now they're not exactly canceling each other, and you'll see light. Okay, so that's the idea. All right. So, okay, so you're going to grab hold of two black holes that are going to spin around each other, and they're emitting gravitational waves, and you're going to detect them. Okay, so this happened. This was, again, these guys had been doing it for millions of years. We saw it the last one, 200 milliseconds before they merged and became a single black hole. That's what we saw. Okay, we could only see it for the last 200 milliseconds. Okay, but they'd been going around each other for millions of years. Okay. All right, so here is 1 meter expands by 10 to the minus 21 meters. So what they've done is, instead of 1 meter, they take something that is 10 kilometers. Okay, it's actually 4 kilometers. 10 kilometers would be 10 to the power of 4 meters, and 10 to the power of 4 meters will expand by 10 to the 17 meters. So it'll expand by the width of a proton. And now we're going to try and measure that. Okay, so here we go. This is in Louisiana. Here's an arm. This light beam travels this distance. This light beam travels this distance. And these two beams combine and they cancel each other. So it's perfectly dark. Now, if this length changes, then the two light beams will not cancel each other. Okay, so as soon as you see light, that means either a truck has driven by or a gravitational wave went by. Did you guys understand that? So as soon as this distance changes, so see, this became longer and this is highly exaggerated, or this, okay, this becomes longer, then you see a light signal. Okay, and like I said, a truck drives by, it shakes the ground, and you see light. So how do we tell if it's a gravitational wave or a truck? So, to distinguish that, remember you spent $5 billion to build that lab? You spend another $5 billion to build another lab. And so if the gravitational wave goes by here, that same wave will go by there. And so if you get exactly the same signal far apart, then what you saw was a gravitational wave and not truck going by. All right, so this was the signal that was recorded in 2015. Okay. Again, so I'll put this numbers in perspective. So here's our sun. Our sun will lose about 1% of its mass, let's say 1 to 2% of its mass, over 10 billion years. That's the lifetime of the sun. It's producing that, okay? So when these black holes merged, essentially they lost 3 times the mass of the sun, and most of the energy was lost in the end within 200 milliseconds. So if your eyesight was, you could see gravitational waves, it would have been an extremely bright event. Okay. All right, you guys, so essentially, so it's shown, again, the energy, the power emitted was, so 2 black holes, one of 36 solar masses and one of 29 solar masses, so 65 solar masses, 65 solar masses, they combine to give you a black hole of 62 solar masses. So 3 solar masses was radiated away, and most of that energy toward the very end, and the power it was radiated, the energy per second radiated was 100 times of all the stars observable in the universe. That's how bright it's shown, and we barely saw it. Okay? Amazing story. So I urge you guys to read the slides, and